So, in the second part of the lecture of week 4, uh, we will be discussing about the shear stress tensor, and that can be broken down into, just to remind you, into two parts: the sigma dash ij, and which is related to strain rates. If different parts of the fluid are flowing at different velocities, so that there is a velocity gradient as a function of xyz, then this part is basically this contributes to the total stress tensor, whereas this part is related to the thermodynamic pressure at uniform rest, because thermodynamic pressure is defined only for a fluid at rest or uniform translation. So we will be basically focusing even last time on sigma dash ij, because we do have an understanding of this isotropic pressure, and we had written down at the end of the class the shear the off diagonal parts of the sigma dash ij, right? The part which is related to relative motion between different layers of the fluid. And for the Newtonian isotropic fluid, there is just one parameter contributing to shear stress, which is uh, eta, which is also called the first coefficient of viscosity, or the dynamic viscosity. There is also a second term which is related to the volume change in the fluid as the fluid moves, and this is called the bulk viscosity. So basically, the sigma dash ij can be written down just as the strain terms could be written down into two parts, one related to volume change, the other related to all sorts of velocity gradients, which is not related to volume change, which was called the deviatoric um strain tensor, right? Now, this part typically for most fluid flows contributes very little to sigma dash ij. Uh, in rare cases, when there are shock waves, so there this term starts contributing, and for this to start contributing, divergence, this is related to divergence of v, which is related to, again, del rho del t, right? So that's how, so divergence v equal to del rho del t. So only if there are very rapid changes in density over length scales, which is the distance between the molecules, does this term contribute. In most fluid flow situations that we handle in daily life, this has very little contribution. But of course, there can be situations when there are very rapid density changes in astronomy or certain cases, and then this term, of course, contributes, and this is the bulk viscosity. We typically, or most people often, when writing down the Navier Stokes equation, the equations for fluid flow, uh, are concerned with this part, the deviatoric part, velocity gradients which do not lead to any change in the volume uh, of the fluid. So they're related to, they're concerned typically with this part, and in rare cases with this part, and that can be written in this shear viscosity into 2 times eij minus 1/3 delta ij. So this was essentially the deviatoric part of the strain tensor, and what you have is this stress is related to viscosity, 2 times viscosity, because this itself comes with a half. If you remember, half del vx del y plus del vy del x. So there's a half, so that takes care of this. So this is related, yeah, to the deviatoric part of the stress tensor. Now, how does this look like? Now, okay, so explicitly sigma dash ij in the diagonal term, I've written down xx, yy, and y dash. Of course, the off diagonal terms are the shear stress, which we relatively easy to understand in terms of flow gradients between two walls, one moving wall and one static wall. But what the reason I wrote down this is essentially there's a double, this is a repeated index, hence there is a summation, hence this term sigma xx gives divergence v, and of course it gives the same term also appears in sigma dash yy and sigma dash zz. However, this term has been broken down here. So you have 2 eta. Here you had half del Vx del x plus del Vx del x. Hence that half takes care of that, and you just have del Vx del x here. The 2 eta is here. And when you expand this, right? When you expand this, you have divergence V. This 2 eta is sitting 2 eta, and this is the 1/3 is sitting 1/3, right? So you have these terms, and similarly you can write down for y in the y direction and sigma dash dash z. So here is what you see is that if there was a volume change, it would also contribute here. So the whole thing as a whole will lead to no volume change. But suppose divergence v was non-zero, right? So if you sum these things up, you will get it, the total sum will be zero. So this is not related to volume change. So if divergence v was equal to zero, but you had del vx del x finite, right? If del vx del x was finite, of course del vy del y had to be uh, come with a minus sign, because this is not related to volume change. This part is not related to volume change. So this could be positive, and this could be negative, so that there is no net volume change. So the flow would be such. Or you could have del Vx del x minus divergence 2 by 3 eta divergence of V. And what does this mean? This is explained very well in page 97 of Kundu. And if there was some uh, diagonal terms of the train tensor, right? And this would basically mean an average over del Vx del y del V del Vy del y del Vz del z. So there's volume change in different directions, and it the stress contributes to over and above that. If one can consider 1/3 to be an average volume change here, or strain rates in different directions, in the diagonal directions, this is taking care that the viscosity will contribute, which is over and above the average, not volume change, because these terms don't contribute to the volume change, but it's like stress in strain in the diagonal directions, a change in velocity in the diagonal directions. This is an average of that, and anything which is an outlier over and above that, that contributes to the stress. Moreover, what I want you to notice is this part also could contribute to the diagonal elements, right? So it's the shear same viscosity which would relate to shear stress, but it also appears in the diagonal elements of sigma dash ij, right? Remember, the sum the sum has to be zero for normal fluids. However, if you have polymeric fluids, you could have these, they could be finite normal stress differences, such that there are finite values between, yeah, sigma dash xx and so on and so forth, but we'll not go into this. So if you sum these things up, it will be zero. Just 1 second, stay in the call. Yeah, so you could have contributions from uh, uh, finite stresses in the XX, YY, and ZZ directions, though the strain will the flow gradient will be such that this part is not, the total volume remains unchanged, right? So that's the message here, and this is how the terms look. Um, the other thing to stress is thermodynamic pressure is defined only when the fluid is at rest. Of course, here we are discussing the part which is not. So, it is this P, right, was the thermodynamic pressure. And when the fluid is in motion, this thermodynamic, you are not in equilibrium. There's a current, there's a flow, hence it is not defined. So what the book by Sonin, which is a very classic, there are lecture notes available on the internet from MIT. He defines sigma xx. Remember, there's no dash here. This is the total one plus sigma yy plus sigma zz by 3 to be the mean mechanical pressure. So if you can get the stress, measure the stress in the diagonal directions and average, that is the mean mechanical pressure. Of course, in reality, this will be, can be very close to the thermodynamic pressure, and we shall discuss with numbers soon. But technically, very strictly speaking, uh, thermodynamic pressure is not defined in flow. This average is called the mean mechanical pressure. However, in physical hydrodynamics book, it is already considering the fluid is in flow, right? And they in that book they call this P to be the mechanical pressure, right? So there's a slight difference in the terminology of the two books. We shall primarily follow this. And since it is already considering things in flow, this is mechanical pressure, and only if there is no flow, this mechanical pressure will be equal to the thermodynamic pressure, right? And this one is the viscous shear tensor. This is called the viscous shear tensor in this book. I would also stress that in Kundu, it keeps on saying this to be the thermodynamic pressure. It will, so this total mechanical pressure will be very close to the thermodynamical pressure, but one should not ideally call it thermodynamic pressure, but it doesn't uh, differentiate. And even Sonin points it out that though Kundu is absolutely an excellent book, it has this slight problem. And I thought, since I'm aware of it, I should make you aware of this. So, yeah, so there should be a dash here. I mean, just to keep the, and yeah. So in Kundu, what it does is basically uh, define sigma, the sum of this. It defines the mechanical pressure, which incorporates contribution from this, and this it keeps calling the thermodynamic pressure, which is wrong. That's all that I want to say. But of course, we are going to refer to Kundu otherwise. Okay. Uh, just to get an idea of what this pressure and what are the stress tensors, what are the values involved, I thought I would just put down the numbers. So one atmospheric pressure in SI units is 10 to the power 5 pascals. What is pascals? Pascal is Newton per meter square. Uh, Newton is 1 kg, the force required to accelerate 1 kg by 1 meter per second square is what is Newton. So remember, 1 kg mass on Earth's surface will give a force of 10 newtons approximately, and which in that case means that 1 atmospheric pressure per unit 1 meter square is giving the force equivalent to 10 to the power 4 kgs. So if you load 10 to the power 4 kgs on 1 meter square, that is the weight of the atmospheric pressure that we are feeling all the time. So that's what 10 to the power 5 pascals means, right? Because on the earth you have 10 newtons. Uh, Sorry, so 1 kg of mass gives a force of 10 newtons, right? So one atmosphere is essentially the same force that 10 to the power 4 kg would apply on the surface of the earth in 1 meter square. So that's a high pressure. Compare, we want to compare this pressure, value of the pressure, with standard shear stresses, mm, which will be uh, experiencing which will be experiencing in daily life. For that, I have written down the air viscosity at 20 degrees centigrade and 20 or 25 degrees centigrade, and that's approximately 2 into 10 to the power minus 5 Pascal second. For viscosity, the SI unit is Pascal second, right? And for water, so water is 50 times more viscous than that of air, and it has viscosity of around 10 to the power minus 3 Pascal seconds at 25 degrees temperature. One does have to mention the temperature, because for water at 100 degrees centigrade, as the temperature is varied from 20 degrees centigrade to 100 degrees centigrade, the viscosity of water decreased by a factor of 4. Okay. uh, on the other hand, the air viscosity, when you take it from 80 to 100 degrees centigrade, actually increases by only 20%. So this would become something like 2.4 into 10 to the minus 5 Pascal second. Note, air viscosity increases with increase in temperature, water viscosity decreases with increase in temperature. And what is the reason? We'll discuss at the end of this lecture. But what I want to tell you, that remember, eta del v x del x, that the diagonal term, uh, it is added to pressure. So eta del v x del x, you can put in down the units of Pascal seconds and check that they have the same units. So the typical, suppose we have a storm. So suppose this air which is moving at very high velocities, and it is being stopped by a building, right? So even so, just to remind you, 10 meters per second is 36 kilometers per hour. So if you have 100 meters per second, you have 360 kilometers per hour. Of course, we don't hardly have storms at that speed, but suppose this 100 meters per second air is being stopped by a building. So the fluid, the air is moving in this direction, and this is x direction. So del v x del x is changing, say, over 10 meters per second. So how much stress is generated, right? And this is basically the diagonal. I'm just looking at the diagonal component. So eta is 2 into 10 to the power minus 5 into 100 meters per second, 360 kilometers per hour. And suppose it is stopping in the walls over 10 meters, even if you put that to be 50 meters, really doesn't matter. This contribution would be 10 to the power 4 SI units. If you want it more, I mean, suppose you say that, oh, suppose it's 50 meters, it's going to be even less. So this contribution, eta del Vx del x contribution, is in the order of 10 to the power minus 4 SI units. On the other hand, pressure is 10 to the power 4 pascals, right? So even if you have very so-called large del Vx del x, it is hardly going to contribute to the pressure, in the change in pressure. I mean, even if you stopped the fluid, if you will measure the pressure, not the mechanical pressure, but the thermodynamic pressure, by stopping the fluid, it would be 10 to the power 5 pascals. On the other hand, this and a very strong would contribute 10 to the power minus 4 to the diagonal terms of the stress tensor, right? Of course, we mostly feel this. And if there was water and you had an Olympic swimmer who was swimming through a swimming pool, this viscosity is 10 to the power minus 3 for water Pascal second. And suppose he was moving, he or she was moving extremely fast, 10 meters per second. So suppose that person is moving his hand. Suppose this is the x direction and this is 10 meters per second, and it comes to rest. I mean, the velocity change is over 1 meters per second. Then also the stress tensor, the component which will be generated will be order of 10 to the power minus 2, 10 to the power minus 3 into 10 over 1 meter. Even if you put it 10 meters, it will even go down further, right? So the relative contribution to pressure in that sense is relatively less. So that's the message wanted to you to have in mind here, just for your ease, so that you can comprehend the whole thing. So here I wrote down only the diagonal terms. I'm writing down, trying to write down the entire stress tensor. From this would basically be eta divergence of v, and you would have identical term for sigma yy and sigma zz. But of course, here we are looking only at the dilatation term, and sigma dash would be sum of the contributions from the dilation terms and the deviatory part of the stress tensor. So this would be the dilation part of the stress tensor. Just to tell you, I have checked that this is at times called dilation. It's also called dilatation. Okay, so they mean the same thing, and both words are used. So the deviatoric part of the stress tensor would look like this. You have a 2 eta sitting outside. You have del v x del x minus 1/3. 2 eta is sitting here, and divergence v. And here you have del v del y minus 1/3 divergence v, right? And here you would have del v z del x minus 1/3 divergence of v. On the other hand, on the other hand, this will be missing when you are looking at off diagonal terms. Hence, you will have a half. Remember, Eij comes with a half, and that's why you have a 2 eta here. So it is half del Vx del y plus del Vy del x. And similarly, half del Vy del z plus del Vz del y. And of course, this is equal to this. This comes from that this part of the stress tensor contains no angular momentum generation, right? So that's what we discussed in the last class. So this is how the entire sigma dash ij will look. These are the diagonal terms. Here also you have some other diagonal terms which is coming from the deviatoric part of the tensor, and these are the off diagonal parts, and of course this is equal to this, and so on and so forth. Right, so this is the equation. Now I've already discussed this. Now with this, now that we have a definition for the stress tensor, we know how to write it down in terms of the pressure, the dilation terms, and the deviatory terms. We finally come to the equation of motion, which is called the Navier Stokes equation. The Navier Stokes equation is nothing but an expression for Newton's equation, m d2r dt2, or m ddt of the momentum in a unit volume. So rho into v, mass per unit volume, into velocity vector integrated over volume. So momentum density, if you like, is equal to any forces, external body forces, which might be acting uh, on that element of the fluid, Of course, this F is, just to remind you, is per unit volume. And if due to the flow there is any stress acting on the surfaces of that unit volume, which could come due to viscosity and other factors, whatever. So I mean, for Newtonian fluid, we take it, we have written down what is the stress tensor. What I want to emphasize is, if stress changes from one point to the other, if there is a stress density variation, there will be a net acceleration of the center of mass of that fluid element. If on the two surfaces of that volume there were equal and opposite forces acting, then the center of mass of the fluid element is not going to change. Now, that's all that is written down. This is the Newton's equation of motion, suitably adopted because you have surface forces acting on that fluid element. Uh, so it's suitably adopted for the fluid, right? And this is uh, acting on all the areas, surface areas, which encompass this volume. Right? So S encompasses the volume V. Now, next, all that we do is invoke the Gauss's divergence theorem. This was an integral over area. And then when we invoke the Gauss's divergence theorem, uh, what we get is sigma ij nj dA. This nj is the outward normal to the area. You get a del del xj, a divergence. This is the divergence. It's taking a derivative of the sigma ij. So hence this equation can be written down as rho f, and here by writing rho f outside, I have assumed that it is you have a practically an incompressible flow, right? Ideally, I should have kept it inside, uh, but this term comes from here. This is this body force term, and now you have divergence of sigma ij, and sigma ij is a tensor. I should have added double line here, but anyway, the ij will remind you that this is a tensor, and this equation holds for any volume element. So in general, we write this as rho f dv dt, rho f into body forces plus divergence of the sigma of the stress tensor. Remember, divergence of the stress tensor is a vector. So if you like, if you want to write any one component of divergence of stress tensor, right? So this is a vector and we are writing this, then you essentially have uh, a divergence of sigma dash minus grad p. Grad p is a vector. You can take the ith component, right? So this is how it can be written down. So this, if I write rho outside dvdt, I have assumed that you have incompressible flow. Note that I'm not saying incompressible fluid, I'm saying incompressible flow, because compressible fluids can also flow or mostly flow in a manner, except in rare cases where you have divergence v equal to 0. Hence, I'm stressing the word incompressible flow. But in general, this rho should be inside, right? So this is taking care of the explicit time derivative. This is the so-called advection term, which appears what Euler would see an element of the fluid getting deformed due to the velocity gradients along. So if Euler was standing on top of the bridge, he would see an explicit time dependence of the momentum on the change in momentum as a function of time, as well as the fluid element flows because of relative changes in velocity. That you would also see the advection term. This is the body part. This is minus grad p These are all vector equations you can understand. So our next focus would be divergence. So how would this term look? Divergence of the stress tensor dash, because I have written the minus grad p separately. Now if you had flow in steady state, there was no explicit time dependence, you would, or for a non-moving fluid, right? If there are no relative velocity gradients, you these terms would drop off. This would also drop off, and this would be your equation of motion. So your grad p would be where did it go? So if there were no relative motion between layers of the fluid, this would be zero. Velocity is not changing as a function of time or space, and then the external force would create a gradient in the pressure, and this is the general Navier Stokes equation. Now for a simple fluid, since we have an expression for sigma dash, the stress tensor, uh, right, the part of the stress tensor which is related to relative motion between fluid particles, we are going to break it down further and look and write it down as vector equations. Remember, sigma dash is uh, this bulk viscosity into delta ij ell plus the deviatoric part. So when you are taking the divergence, each component, so basic, so this is a tensor, and the way you take divergence is take a row, del del x of this, del del y of this term, and del del z of this term. Note del del xj, and here you have ij dash here, repeated index j and j here. So that corresponds to del del x of sigma xx, del del x, del del y of sigma xy, because you have this index and derivative with respect to y, z index and derivative with respect to z. And if you do that, that is essentially a vector. I mean, it's basically, if you look at the x component of the, so this is a vector, and here we are looking at one of the components, the x component of the divergence of sigma dash tensor. In general, if you are focused only on the x component, you're taking a derivative. This is the this will be in the diagonal, hence you're taking a del del x of this term, right? Then del del x of whatever will appear from here, the diagonal term. Just to remind you, we're taking del del x of this. This is the deviatoric part, this is the dilatation part, right? So we're taking del del x of this as well, del del y of this term, and del del z of this term. That is exactly what I've written, del del x from this term, del del x from the diagonal part of the deviatoric part of the stress tensor, del del y, 2 eta into del del y. This is taking derivative of sigma. So 2 eta, if you put in, it's sigma xy. And this is taking derivative with respect to z, sigma xz, right? Because del v x, del z, del v z, del x. And of course, it comes with a half, and you have a 2 eta here. So basically, when you take the divergence and you take the x component only, this is what you get, right? This is the x component uh, of it, and this can be simplified. So this I have just written in black, right? this so it's a del del x of these, this, this, and one term from here comes here. So this essentially, so remember there's a 2 eta here. So 1 eta del del x of del v x del x comes here. Okay, and there should be an eta factor here also. So this eta should be here. Here in general you have your yeah, this 2 cancels, this del v y del x del v y del x, and remember there is this del y, it can be interchanged. So these blue things are coming here and the purple things are coming here. Okay, so you will see that del del z, the double derivative of z vx, double derivative of y acting on vx, and double derivative on x acting on vx, so it has come here. Okay, so yeah, and you have also a divergence v sitting here, remember that, right? uh, so so here you'll get 2 eta or 2 by third eta divergence of v, which will also be there. As a consequence, you are going to get zeta plus eta by 3 grad of divergence v. So if you just check out the terms, you will get this this one. So this, remember, is now written as the vector equation. This was one of the components. We are writing down the x component only. So if you just work this out, you will get this equation. Eta grad square v, which is essentially eta grad square v. This was only x component. Here I'm writing as a vector equation, right? In addition, you will get this term when you arrange, when you take care of all the terms. So this is what the simplification will be. And if that is your divergence of sigma dash, here I've explicitly also written down the y component. Uh, so in tensor notation, it can be written down as eta into del. So basically diverge grad 2 vi, because I'm writing down the ith component, del x j. I mean, it's this Laplacian acting on a component, because this is repeated index. And this term, note the here again you have repeated index, you have repeated index there. Uh, so you can write it down. So in general, the Navier Stokes equation basically plugging, so plugging this here, this is your full Navier Stokes equation, where I have written down explicitly the Laplacian acting on V, and it acts with, it comes with the shear viscosity coefficient, and this will also contribute if divergence of V is non-zero. But typically, if you are looking at incompressible flow, these terms are not going to contribute. If you only have really compressible flow and you have very high velocity gradients over extremely small length scales, will this contribute, right? So typically the equation that you see is this black part, but remember the blue part also exists. though it is typically neglected, and there are valid reasons for doing that. So this will come only if compressibility effects are not negligible. What are the boundary conditions for flow at solid walls? So that's your partial differential equation, the Navier Stokes equation. But now that has to be supplemented with boundary conditions uh, for you to be able to solve the equation. And we will consider right now only solid and fluid boundaries, because if there are fluid boundaries, there will be extra complication of surface tension. When two fluids flow past each other, there will be a surface tension difference, and that will add to the complication. So today we're going to just discuss, suppose there was a fluid, and so this is fluid, and the and you have a fluid flowing past a wall. Then the fluid cannot enter the solid, so the normal component of the normal component of the velocity of the solid has to be equal to the normal component of the velocity of the fluid at the wall. Moreover, if you have stick boundary conditions, if you have finite viscosity and at length scales much, uh, so one considers that if there's a solid wall in motion, the fluid is going to stick to the surface of the solid, and it is going to have the same tangential component. So the fluid is going to stick and move with the same velocity as that wall is moving at that point in space and time. Hence, this tangential component of the fluid, of the velocity of the fluid, is equal to the velocity of that solid surface. Normal component is equal, so that fluid cannot enter the solid. The tangential component means that the fluid is sticking to the surface and moving along with the solid. Remember, this is valid only for viscous flows, and one could not write down such a condition, the second condition, the tangential component condition, for Euler flows, because there was no viscosity, there was no reason for the fluid to stick to the surface of this solid. We actually didn't use this at all. If you notice, we use this, but we didn't use it for the Euler flow. The last thing to discuss is basically the why the viscosity of air increases when you increase the temperature, whereas viscosity of water decreases as you increase the temperature. So viscosity has so what is viscosity? As we discussed in the past, or we briefly mentioned in the past, and we're going to discuss this further. um, the kinetic viscosity, or eta by rho, is something like the diffusion constant of momentum. Now, diffusion can occur in two ways. Diffusion of momentum can occur in two ways. Uh, Suppose you have a fluid, then and you have molecules inside the fluid. So you have fast moving molecules. I'm not talking about fast flowing fluid. I'm talking within a certain volume, you have fast moving molecules, and they can move and transport momentum from this part of the fluid to another part of the fluid. That's what happens in air. There are relatively rarer collisions. There's a lot of free space between the air molecules. So fast moving molecules transport momentum because they have momentum by moving from one place to the other, and thus there is a transport of momentum, which is characterized by viscosity. The rate of transfer is characterized by viscosity, kinematic viscosity actually, eta by rho. On the other hand, for a liquid, in a liquid, what happens is they are all sticking to each other, and basically each molecule is surrounded by many other molecules, and they're constantly colliding. So the the transport of momentum in a fluid element, which itself consists of large number of liquid molecules. What happens is a fast moving, so here the fluid is in motion, the molecules are they are moving in all random direction, but there's a net slightly higher motion, suppose in the positive x direction. Then as it collides with other liquid molecules which have a lower velocity in the, suppose the x direction, it transfers some of the momentum to it. Remember, we are still looking within a small fluid element. We're not talking about relative velocities of the fluid. Well, we are. In the second case, we are, because they're densely packed. Molecules are colliding, which are moving with a slightly higher velocity in a particular direction, slightly higher with respect to the fluid motion. By virtue of collisions, transport momentum. In air, it is the molecules themselves are going from one place to the other and transporting momentum. So this is different. This mechanism can be different of the way of momentum transport due to viscosity. And number, which is the kinematic viscosity, and it has dimensions of L square by T, and the ratio of kinematic viscosity and the mass and the diffusion constant is called the Schmidt number. Now, if Schmidt number is extremely high, if kinematic viscosity is much higher than D, the diffusion constant, then essentially it means that the momentum transport is primarily by collisions. On the other hand, if Schmidt number is very low, that means D dominates, then essentially the momentum transport uh, by the fluid is primarily, if D is dominant, then it is primarily like that of air. So air, there are large collisions. When you have a large number of collisions and air molecules move a large distance, around 50 nanometers actually, if before they undergo collisions. That's a basically mean free path of air molecules. You can check it out from your kinetic theory. There, if you increase temperature, the velocity of the air molecules increase, and there are more frequent collisions, which leads to increase in the viscosity. On the other hand, for a liquid, what you have is when you have a higher temperature, uh, the liquid molecules uh, undergo, they also gain energy, they undergo more collisions and change its neighbors. They're able to change its neighbors more quickly, because here attractive interaction between between water liquid molecules is also acting, and it is able to overcome its attraction due to its potential energy, attractive potential. In that, in the case of a liquid, it is more easily able to overcome the attraction coming from the potential, and thereby, as you increase the temperature for a liquid, viscosity decreases. The mechanism is very different. Hence, the viscosity in one case increases with temperature, that is air. On the other hand, it is an activated process actually in case of a liquid, and their viscosity decreases hugely. Just to have an idea um, of the numbers, eta, the kinematic viscosity, is the dynamic viscosity. So this is suppose nu. Uh, this is the dynamic viscosity by rho. And as I told you, eta has values of 10 to the power minus 3 SI units, which is Pascal seconds. Rho for water is 1000 kg per meter cube. That's the density of water, right? And and you can check that nu has dimensions of L square by T. Just check it out for yourself, right? And so you can see that in 1 second, the momentum diffusion, so I said this is a coefficient for momentum diffusion, is uh, so this will have values of 10 to the power minus 6. This will have values of 10 to the power minus 6. And if you write down nu t, so this is what I've done, nu is 10 to the power minus 6 into t equal to L square. Then in 1 second, the length scale over which you will have momentum diffusion is square root over this, which is 10 to the minus 3 meters. 10 to the minus 3 meters is essentially 1 millimeter, right? It's just 1 millimeter. So in 1 second, for water, it will move momentum diffusion. I mean, the length scale over which momentum will diffuse is order of 1 millimeter. And if you have microscopic particles, micron sized particles, then that length scale of the length scale over which there will be momentum diffusion is actually 1 millisecond. D for water, you can check it up. D for water, diffusion constant for water is 0.001 millimeter square per second. So if you take the ratio, you will immediately get the 10 to the minus 6 by 10 to the minus 9. It's like a very large number. Hence, for water, you know that the momentum transport is primarily by collisions and not mass transport. You can do a similar calculation for that of air, right? So that's where we should end this.